Hello, my name is Wu Qiang Yang. I come from University of Manchester in the UK. I'm a fellow of AET, fellow of Institute of Measurement and Control, and fellow of IEEE. Today, I talk about electrical capacitance tomography from principle to applications. Electrical capacitance tomography, in short, is ECT. I separated my talk into 4 parts. Principle of ECT, AC-based ECT system, industrial and medical applications. In the end is a summary. Let's start from part 1, principle of ECT. The basic principle of ECT I can summarize in 3 bullet points. We talk about capacitance tomography. Obviously, it is based on capacitance measurements. We measure an industrial process or medical subject from many different angles. The objective is to reconstruct permittivity distribution. Here is a typical ECT sensor with 8 electrodes. From this sensor, we use this formula, we can work out, we can have 28 independent capacitance measurements. We talk about measurement, we start from a sensor. Here, I show you 2 typical sensors. One is a high pressure sensor up to 100 bar. One is high temperature sensor up to 1000 degrees. For sensor design, I published a paper in 2010. This paper so far has been cited 287 times. With the ECT, what we like to have? If we have this type of distribution, like 1 object, 2 objects, a more complicated distribution, we expect we can get this type of image. Now, from the image, what we can get? We can get material distribution or permittivity distribution. From a permittivity distribution, we can derive the concentration, we can derive flow rates, or even flow regime. We can see flow dynamics. For some applications, we can work out flow velocity and flow velocity profile. Our final objective is to convert non-measurable process into measurable process so that we can control the process. There are many different types of tomography systems. ECT is one of them. I can summarize the advantage of ECT in the following part. Non-radiation, non-intrusive, non-invasive, which is very desirable by industry. Fast, the typical speed is 100 frames per second. In terms of sensor or process, the dimension is flexible. Can be small, can be large. The smallest diameter I did is 8 millimeter. The largest diameter I did, 1 meter in diameter. It is robust, can withstand high temperature and high pressure. As indicated by previous slide, I showed you 2 sensors. It is also low cost to compare with such as X-ray, gamma-ray systems. To design a tomography system, like ECT system, there are some challenges. In hardware, we have to measure very small capacitance down to 0.01 femtofarad. Normally, we use a picofarad as the smallest unit, but now we need a unit femtofarad, which is 1,000 times smaller than picofarad. We need the speed, we need the signal-to-noise ratio, high signal-to-noise ratio. In mathematics, there are also some challenges. Between capacitance and permittivity, the relationship is non-linear. We need to deal with non-linearity. It is an underdetermined solution. It is a year-pose, year-conditioned problem we have to deal with. In engineering, we have to consider scale up, scale down. We have to re-engineering sensors and systems so that we can work in particular environments. For some industry, we need to consider intrinsic safety, we need to consider explosive proof, we need to consider attacks. We talk about tomography. Image reconstruction is commonly known as a mathematics problem. What is the image reconstruction? Image reconstruction basically is we divide the imaging area into many small pixels, such as 64 by 64 pixels. In this case, we have nearly 4,000 pixels. Do remember, we have 28 unknowns. We need to solve 4,000 unknowns. Yeah, we have 28 knowns. We need to sort out 4,000 unknowns. So the task is we have to assign permittivity value to each pixel in the imaging area according to capacitance measurement. This is called solve inverse problem, commonly called image reconstruction algorithm. There are many different types of image reconstruction algorithm. Here I list a few of them. Let's start from a simple one, like a linear backprojection. Little bit more complicated, like Tikhonov. More complicated, like a Newton-Raphson. Landau-Weber. Now in the future, we can consider whether or not we can make use of neural network, deep learning, even AI for image reconstruction. In 2003, I published a paper on this topic. So far, this paper has been cited 1,000 times. I move to part 2, AC-based ECT system. Here I show you a typical ECT system. In this system, we have 16 measurement channels in parallel operation to achieve speed. The speed is typically 100 frames per second up to 300 frames per second. The signal-to-noise ratio is 73 dB. We have a user-friendly interface. Here is the interface. For a person who have never used this system, for 5 minutes, he or she can manage this interface. Recently, we developed real-time 3D imaging software. With this software, we can see a flow in 3D structure in real time. In hardware design, I published a paper in 1999. So far, the citation is 312. This system has been used in many challenging applications by companies, by research organizations, by universities. Here I give you some ideas who are using our tomography system, our ECT system. Those users include some big names like NASA, like Schlumberger Oil Company, like Airbus, like Rolls-Royce, and some universities like Tsinghua University in China. Also some Chinese Academy of Sciences, they use our tomography system. Here I just give you 2 examples of applications. One is industrial application, the other is medical application. For industrial application, this example is about gas oil water flow measurement. So far, in oil industry, this is a still challenging topic, how to measure gas oil water flow accurately. We worked with Schlumberger Cambridge Research on this topic. This is a sensor we developed. This is a multi-modality gas oil water flow meter. In this design, we have several different operation modes. We have ECT, we have a microwave, we have ultrasonic, Venturi. This is a multi-modality measurement system. Here, I give you 2 typical results. One is horizontal flow, gas oil water flow. This is a vertical flow. That means the liquid or gas, the oil from bottom to up. We published a paper on this topic. This paper so far is 61 times citation. In medical application, this example is about revision heat replacement. Heat replacement, this is a big task in the UK, maybe because of lack of sunshine. Every year, about 75,000 people need this operation. In 10 years' time, about 10% people need a redo. This is quite a painful operation. So this picture here shows you hip replacement. You need to replace this part by a ceramic or some other materials. People dream to have automatic tool to drill your bone accurately. But in fact, now automatic tool is not reliable. So people don't want to use an unreliable tool to do this. Also, there is no real-time imaging tool to do this. Our objective is to develop a real-time navigation tool for this purpose. On this topic, we published a paper 2016. If you are interested, you can read this paper on IEEE transactions, instrumentation, and measurement. Now I move to the last part, is my summary. ECT is the most mature industrial tomography system and also useful for medical applications. Already, there are many applications of ECT, in particular for multi-phase flow measurements. From my talk, you can see ECT is a useful tool for understanding complicated processes, to verify simulation, model simulation results, and for measurement and control. ECT has been used in oil gas industry, in pharmaceutical industry, power industry, and many others. In future, what we like to do on this topic, we like to work on multi-modality system further. For example, combine ECT with electrical resistant tomography, combine with magnetic resonant cavity sensor. We need to further work on post-processing, such as by big data, by deep learning, by AI, those are modern topics. Thank you very much for your attention.